Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, welcome to the tutorial for week 4. We are going over the homework solutions this week. The first problem had to do with the heat balance equation, and the goal was for you to derive the second derivative of the temperature and see how heat generation per unit time and volume are related. The derivative of the heat per unit time is related to the heat flux that from neighboring units, derivative with respect to space, and the unit of heat generation that is happening at that location, which is given by Joule heating, the heat current, the electrical current times electric field. We should also always remember the coupled charge and heat transport equation. These are the ones that you saw in week 2 in Mark Lundstrom's lectures. The heat current is proportional to the electrical current at derivative of temperature, and electric field is also proportional to the same parameters. So the first thing we do is the JQ on the first relation replaces JQ here, and electric field here replaces the second term. That way we have Q point, the derivative with respect to time, now is the derivative with respect to space of this term. In this term, we assume Seebeck coefficient doesn't change with distance. Electrical current is continuous, is constant, so that doesn't change. The only derivative term is derivative of temperature. And then this one, the second term, gives you the second derivative of temperature when you apply this operator. Then in the second term, you just multiply everything by JE, so it's JE squared divided by sigma, and there is a JE here. This equation is easy to simplify as these two terms cancel, and all you have is second derivative in space and the amount of current squared divided by sigma, which is the Joule heating. At steady state, the change with respect to time is 0, and it gives you a steady state equation for current. This equation is quite simple, as the second derivative of temperature with respect to space is now a constant, because basically Joule heating is constant per unit distance. Now let's solve this for a specific boundary condition. The boundary conditions we are applying is the current flows, and then we have at position x equals 0 temperature is given by Tc, and position x equals d temperature is given by Th. This is the equation we had just in the previous page. This is second order derivative is proportional to a constant. The solution of this is quite simple. The first order derivative is this constant time distance plus another constant, and then when you take another integral, then you get the x squared, 1/2 of x squared, the same coefficient as here. Then this constant which comes from the first derivative is now has an x, and then a second constant. So this is the general form of a temperature as a function of x is a parabolic equation. The two constants depend on boundary conditions. We know the two boundary conditions, x equals 0 and x equals d. We put it there, and from that we find coefficients C1 and C2, and that's the expression for temperature x. That gives you again how temperature in a thermoelectric element changes based on the Joule heating inside. We haven't yet put anything in terms of the Peltier effect at the interfaces. So how this looks graphically, at I equals 0, there is no current flowing. As expected, temperature is a linear temperature drop between the hot and the cold side. Voltage is also linear drop. This is just basically verifying that the equations are consistent. Now, if the current is non-zero, the solution from previous page gives you a parabolic equation for temperature profile. The chemical potential and voltage also follow similar equations, and that's what is happening inside a thermoelectric element. Now, in order to study what happens due to Peltier cooling or heating at interfaces, we need to look at the equation for heat flux out of the thermoelectric element due to what is happening inside of it. Is related heat flux per unit area could be put on the other side, is the derivative of temperature with respect to x at that position multiplied by thermoconductivity. You remember from previous problem 1-2, the expression for temperature was fully determined by the properties of the thermoelectric material, its electrical resistance and thermal conductance, as well as dimension. You put this derivative with respect to x, and then put x, which is here, then you put x equals 0. That's Q out. Q out has two terms. When you multiply thermoconductivity area divided by d, you get the definition of thermal conductance, and you multiply by the second term, basically the conductance and thermoconductivity disappear, and you get 1/2 Ri squared. This is the famous 1/2 that you see in a lot of thermoelectric studies. Half of the heat goes to the hot side, half of it goes to the cold side. Really can be derived using this microscopic equation. Now we say, what is happening at the cold side of thermoelectric is there is Peltier cooling that is happening at that location, is a localized source of cooling, which is St cold times I, plus amount of heat flux, which is determined by this, and the amount of heat flux determined by this is this equation. And again, this is used a lot in thermoelectric heat balance equation. Cooling at the cold side is the amount of cooling minus half of the joule heating minus heat conduction. So by doing this from a microscopic point of view, now you can change some of the parameter and see the impact what is happening inside. One parameter could be what happened in a quasi-ballistic thermoelectric cooler device. You saw in earlier lectures in that week 4 that the energy deposited by electrons when they are emitted over a barrier, it takes a distance on the order of, let's say, 1 micron for gallium arsenide for electrons to lose an energy equal to an external electric field. Electric field applied was 5 volt per kilovolt per meter Kelvin, and here is the external electric field, and here is some sort of a fitted curve. When you do fitting, there's always small errors because this is Monte Carlo with 5,000 electrons, so you have some errors related to that, but approximately you get this type of fitting. So comparing to the previous case where second order derivative with respect to temperature with respect to distance was just a constant joule heating, now the joule heating has a spatial dependence, is a constant 1 minus exponential this. This is this red solid curve here and what is given here. The question is, before, without this term, we solved this differential equation and we know what is the balance. Now with this term, how can we solve it? Again, we have two boundary conditions, temperature on the cold and the hot side are given at the two sides of the barrier. Here are the equation is again written in this form. What we do is second derivative with respect to space is shown by t double prime. We introduce a constant b, which is given by this coefficient because we just don't want to write that coefficient many times. Again, this coefficient can be written as a function of ratio of the electrical resistance to electrical conductance of the leg, current square divided by thickness of the barrier. If this is the second derivative with respect to space, first derivative with respect to space is this form. Basically, there is a lambda e that comes here. B become b times x, and there is a constant. Basically, derivative of this is this. Simple. But then you take from that another integral to calculate temperature as a function of distance, and this exponential term give you another lambda e, become lambda e square. Bx give you 1/2 bx square. C1 give you cx, and there is another constant which is coming, and that constant is tc minus b lambda square. How do we know that? Because at x equals 0 we should get tc. X equals 0 to give you 1 here. This and this cancel and you get Tc. How do you calculate Th? That's at x equals d. It's a little tedious, but it's a straightforward math. In the expression for t, you put x equals d. So you have a first term, d divided by lambda exponential, then you have a d square, then you have a d, Tc, and so on, and that all of that should be a Th. At the end, what we are looking for is an expression for C1, because that's the parameter that we were looking for. And the C1 we can find through this balance, again, is shown here. And you can simplify this even further by looking C1 in this form. Is a long form, but C1 and C2 are the two coefficients. Now I know temperature at every position in a ballistic barrier is exponential form, very kind of complicated, but it's good to verify the limits. Remember also the B was introduced in previous page just because of the simplification in notation, and that is also as a function of material parameters as well as dimensions. So that's the expression that you have to find in your homework. Again, it's a long expression, but step by step is straightforward. It's a solution to a second order differential equation. Now let's do the same thing with a ballistic heater that we did with a conventional thermoelectric. We calculate the amount of heat flux at x equals 0. Again, heat flux per unit area, thermal conductivity divided by, multiplied by dt dx at x equals 0. From the previous page, we calculate dt dt with respect to x is a long expression. We put x equals 0. There is some simplification could be done. You multiply by kappa A, and that's you Q out. So Q out for a ballistic thermoelectric is Ri square plus multiplied by this term plus K delta T. It's very similar to what you had for a diffusive device, but for diffusive all you had is 1/2. All of this, it comes because electrons are ballistic in the barrier. Not all of the heat is deposited uniformly everywhere. But one could verify that this converges to 1/2 when lambda E divided by D goes to very small numbers. Here are again the expressions for this. This is fraction of Ri squared that goes to the cold side. Here is mathematics, but even intuitively you would understand that I'm injecting the carriers from the cold side to the hot side. It takes a carrier some distance before they release energy equal to what they deposited. And as a result, how much of this volume generated heat due to the Joule heating in the barrier comes back to the cold side is not the 1/2 we had before, is less than 1/2 because of this ballistic point. If you put the numbers there, again, you know, with some, if you don't know what is the applied field, you only look at the Monte Carlo result. You say the average field was 4.8, close to the 5 applied. The distance for which the exponential drops by 1/E factor is 200 nanometers. So distances over which the amplitude goes from 4.8 to down to 3, that's 200 nanometer. The barrier thickness is 3000 nanometer, 3 micron. So the ratio of lambda E divided by D is 115. You put 115 in this expression, everything depends only on this ratio. What you get is this coefficient for Joule becomes 0.44. All of this is to tell you, in the case of this ballistic barrier, instead of 0.5, half of the heat going to the cold side, a little less than that goes to the cold side, 0.44. If the barrier is thinner, the fraction that goes to the cold side is even smaller because the heat is mostly transported ballistically. And this expression can give you all the ranges of the barrier thicknesses. Now let's look at this problem number 3, where we look at energy balance in a device. And for that we take a thin film cooler where you have a device, T1 is temperature on top, you have sitting on a substrate, top contact is shown. Here is for completeness, we want to show you whenever you send a current through a device, there is an electrode and heat conduction, Joule heating in the electrode could dominate. But in this problem, we neglect that. It's just is there to show you something is there. You need to worry about it if you do realistic calculation, but to the first order we can eliminate it. So what is the net cooling that happens on top of a cooler? This is the expression we had. Net cooling, if there is no heat load, is 0, is Seebeck times temperature at the cold side times current minus 1/2 Ri square minus heat conduction. From that you find expression for delta T. The delta T across the device has a term proportional to I square, has a term proportional to I. You can write that, you can make it as a quadratic equation for I by doing I minus STC divided by R square plus a constant. The advantage of this is you can see right away that the maximum ZT delta T you can get across a device is 1/2 ZTC square, and you see the optimum current that give you that is when the current is S times TC divided by R. If you're not comfortable using this type of completing the quadrature, all you can do is take the derivative of this delta T with respect to current, find optimum current, which is this one, put it back, and then you get this expression. There's no much detail, so this is the expression used all the time by thermoelectric people. And now you want to use some simulations to verify that. In the simulations, again, this is a big picture of what is in the simulation. You can simulate everything in this, meaning different sizes of the thin film, different sizes of the substrate, electrical conductivity, Seebeck, and thermoconductivity on each layer could be given, the current flows, and even three-dimensional heat spreading in the substrate is calculated using the analytical approximation described in the online simulation. To do this part of it, you go under nanoHUB, Tools, Thermo, and you get to this page, and this page gives you an introduction of what is the tool. It can give you cooling for a single element or a thin film device, as well as a power generation module. You click here to go to the next phase and select conditions. When you click here, it gives you this. First, you have to choose which mode, because you can use the same device under different boundary conditions. This mode tells you what are the variables, what are the boundary conditions. Mode 1 is thermoelectric thin film cooler. Cooling power is known, meaning that we put a known cooling power on top, and our goal is to calculate temperature on top as a function of some parameters, for example, current. Here you enter the input current, cooling power density. It says 0 watt per centimeter square. You input the ambient temperature. Then you input what is your independent variable. You want to plot something as a function of something. When you simulate this as a function of cooling, what is the parameter you change? Let's say current, and you're changing between 0 and 2 amp, and there are increments of 0.01 amp. When you do that, the next phase of this, you can decide to include the substrate or not as a first order, just to understand how a single leg works. Let's remove the substrate. The figure drawing will be updated. Remove the substrate. Again, these electrodes are shown for completeness. The heat leakage through that is neglected in this simulation, can be added by the references to explain in the website. What is good is that through this graphic interface, you can change property of each layer. You see a little blue dot next to the name of the contact resistance thin film property. You click on it, and for example, thin film property, then you can put the numbers by hand. What is the Seebeck coefficient? 200 microvolt per Kelvin. What is the thermoconductivity, electrical conductivity, thickness of this layer, 50 microns. What is the area? 10,000 microns squared. That's 100 by 100 micron. You can enter the contact resistance. From that, you can calculate a curve such as this. So end result, when you run the simulation, you can calculate the temperature on the cold side versus current. This is a dynamic curve that is given by the simulation software, has lots of information in it. By just clicking different location, it gives you a value at that of that curve. So you can actually use this curve to study some of the numbers. If you're not comfortable with this user interface, you can go there and download the data in an Excel or other type of formats and just plot it. What is the result? First thing is you get a result that is as expected. At 0 current, the temperature on the cold side is 300. You don't do anything, temperature is ambient. You send current. First, the temperature goes down because you're cooling, because of the Peltier effect. Cools down to some numbers that you can check here, 250 degrees or so, at about 1 amp for these dimensions. And then at some point, Joule heating dominates our Peltier cooling. I square terms is bigger than I, and this goes up. You can exactly calculate what is the delta T max from the output of the device is 58.4, the optimum current is 0.97 amps, and you can check if these numbers that the simulator give you are accurate numbers. So let's check it. If I put this number of cooling, the temperature on the cold side is 241.6. Let's put this. Z number for this material properties that we inputted is 0.002. We calculate 1/2 ZTC square, which is this number, 58.4. That's exactly what we calculated by the simulator here. So you see that is self-consistent. One thing to know is the equation delta T equal 1/2 ZTC square is used a lot in thermoelectrics, but sometimes people do not pay as much attention. Delta T is T hot minus T cold. So this equation has T cold on both sides of it. If you guess T cold, you put the 1/2 ZT square T cold square, and from that you calculate T hot minus T cold. But you don't need to guess it. This is an exact equation. This is a second order equation for T cold. You can solve for this for T cold only as a function of Z and T hot, and it's valid for every T cold. So this is something that you can use all the time, so you don't need to guess the value of T cold. If you use this directly, you can calculate delta T max without kind of doing iteratively. What happens when you add parasitics? Again, on the simulations is easy. You go back in the simulation and you say, let's add a contact resistance, 1 exponential minus 6 per ohm centimeter square. Ohm centimeter square, that's the contact resistance. This is actually a good contact resistance, but because it's a thin film device, 50 micron, still reduced amount of cooling. What is the advantage of the graphical user interface? You can see the previous cooling and the new cooling, so you can see it on top of each other, and as long as you haven't cleared previous graphs, you can see everything on top of everything. Again, on each of the curves you can click. When you click, it gives you temperatures and currents, so these are interactive graphs. There is a little bar on the bottom of the simulation. If there are two cases, you come in one case, basically one curve become active, you go to the other case, the other curve become active. If there are 10 different curves, there will be 10 different points. You can make each one of them active and look at the data around those. When you add contact resistance, the result makes sense, the cooling is reduced, but by looking at it, you already can learn even more. So you see the cooling is reduced from this point about 58 degrees to about 46 degrees. But what is interesting is the beginning of the curve, the slope at the beginning has not changed. Why? Because when you change contact resistance, you affect joule heating, which is I square. At very small current, the linear term, which is proportional to the Seebeck coefficient, has a change. And that's a good indication that simulation is right. And even in experiments, if you have curves where theory and experiment are different because not what is happening at the beginning, you say at least my predicted Seebeck ratio with thermoconductivity is the same as what I expected. Everything that changes the quadratic term could come from parasitic joule effects because these are I square. What happens if now you add a substrate? So again, now you have 3 simulations, you go back and you add a substrate with a realistic numbers properties. The cooling is reduced a little bit. 58.4 became 46.1 with the addition of contact resistance, but 46.1 only become 44.5. Only a little change, about 1.5 degree reduction. Why? Because substrate, you can see the effect, is not a big impact. When you do the simulation with substrate, not only you see the temperature of the top side, you also see the temperature on the bottom side of the thin film, because now instead of being an ideal heatsink, is a substrate that has a finite thermal resistance. And again, that's something you can verify. You can see that at the optimum cooling, substrate heats up a little, about 1.9 degree. Why? Because at the junction between thin film and substrate, there is a Peltier heating at that interface. There is also Joule heating in the substrate, depending on the conductivity of substrate. That also could dominate, and these are the factors one has to consider. Now let's look at the next problem, problem 4, which had to do with segmented thermoelectric element. In this lecture, you saw that in a single material, delta T max is 1/2 ZTC square at this optimum current. And at this optimum current, I square R and STCI cancel. Basically, Joule and Peltier effect cancel. And of course, that's what gives you maximum cooling. The question is, if I have two segments, the Peltier effect at the first segment, assuming the Seebeck of the metal is 0, is S1 times T times I. The Peltier at the second junction is S2 minus S1 times T times I, because it's always proportional to the Seebeck difference. We want to do in the same second leg similar thing, so we want S2 minus S1 times Ti to be the same as S1 times Ti. Basically, the only way to do this is S2 becomes twice S1, is like a step increase as S1. If S2 is become twice S1, but sigma 2, the conductivity of that layer is 1/4 of sigma 1, still S2 sigma 2, the power S2 square sigma 2, power factor of the second leg is the same as S1 square times sigma 1, power factor of the first leg. But I made the legs, the second leg, quarter shorter so that the two resistances are the same. Thermoconductivity is the same. So now I have two legs so that they have the same power factor, the same thermoconductivity, the same ZT, and the same resistances. And the claim was, this is better than just material 1 with the same power factor, frame ZT cooling. That was the main lesson in that lecture. We want to verify if this is true using the simulation. All you have to do in the simulation is, you assume you neglect the heat spreading in the substrate. If you neglect heat spreading in the substrate, it becomes like a leg similar to the top leg. Again, this is shown that there should be some contact on the side, but shouldn't confuse you. This is not included in the calculation. What you have is one leg, another leg, the thickness, Seebeck, conductivity, thermoconductivity, everything are given, can be changed, and you assume the same numbers you assume the same dimensions, but different Seebeck and conductivity for the two legs. This calculates the heat balance equation as a program, and you can see how much the cooling it is. Here is the cooling we had previously, and here is the cooling we have with the two leg elements. And what you see is that instead of 58.4 degrees, now the cooling have increased to about 72 degrees. Significant improvement just by keeping the two legs without increasing ZT. That was one of the main conclusions from that lecture on segmented elements. And this heat balance equation gives you exactly that. What you see is that you're able to cool better by pushing this cooling at even a smaller current, because now you have a distributed cooling inside thermoelectric element. In problem 5, we took the same device, but we looked at power generation. So the difference is now, instead of sending a current, there is a temperature difference, and this is connected to a load with resistance RL. The question is, how would you analyze this? Well, this is like when under a temperature difference, thermoelectrics is like a small battery. It generates an open circuit voltage, which is given by Seebeck coefficient of the thermoelectric times the temperature difference across the thermoelectric element plus Seebeck of the substrate, because now we have a substrate plus the temperature difference across the substrate. That's the total voltage generated by these legs plus substrate. But there is an internal resistance, which is given by resistance of substrate, resistance of thermoelectric, and resistance of the contact. All of it is now connected to a load, and what you want is to maximize power going out. Ohm's law, V open circuit, give rise to a current. which is total resistance plus resistance of the load, and open circuit is S of thermoelectric sum delta T if you neglect the substrate. From that you can calculate the current flowing from this equation, and power out is voltage current flowing square times RL. So from that you can calculate this. That's an important equation, but tell you how much the current out changes as a function of delta T, is always delta T square, and as a function of R load. But we have a choice to change R load. So here is again expression for P out. Which load resistance maximizes this? In order to maximize our load, we take derivative of this with respect to our load. You make it equal to 0, that's the extremum. At that extremum, resistance of the load should be equal to resistance of internal. Not that surprising, like any internal regular battery. You put this in the expression here, and that's the total power out. Total power output from a thermoelectric, again no substrate, this only depends on the Seebeck coefficient, resistance of the thermoelectric, and delta T square. Thermal conductivity doesn't come here because that's part of what is required to establish delta T and the efficiency, but not as a function of the power output. Now let's calculate the efficiency. The efficiency of power generation is the amount of power generated divided by total amount of work. Power generated, I told you that is current times voltage. This is S times delta T is total voltage generated, and IR is the internal resistance of this thermoelectric. That's the amount of loss. We cannot get power out of it, so that's the total net power generated, and STI minus 1/2 RI square plus K delta T is the total work needed to operate this. This is the efficiency. This changes with current. Let's calculate the optimum current. You take derivative of this with respect to current equal to 0. It's a little tedious, but you can easily calculate the current. The optimum current at the end is given using some simplification by S delta T divided by R gamma plus 1. And where gamma is introduced is 1 plus ZT M square root of it. And ZTM is the average temperature between cold and Tm is a temperature of the hot plus temperature of the cold divided by 2 is the average temperature across the thermoelectric element. Again, all of that can be calculated using simple algebraic relation. So now that we have the expression for I, the optimum load for maximum power is gamma times R, is not R anymore. 1 times the square root of ZT comes in. Here is the expression for gamma max. And this gamma max is important factor. When can we get from here to Carnot? Carnot is this number. So we get to Carnot when this factor is 1, when this equal to this. When these two are equal is when gamma is infinity and when the z goes to infinity. So basically this proves as z goes to infinity, the maximum efficiency goes to Carnot factor, which is makes sense because Carnot is the highest efficiency one could reach. In problem 5 and 6, you can calculate the maximum power as well as the efficiency of a thermoelectric power generation by systematically changing the load. This is a very instructive graph because you see if the resistance of the load is very little, you get little power out. Why? Because you get lots of current with tiny voltage across a tiny resistance at the load. That's not much power. If on the other hand load resistance is very large, you get large voltages across of it, but then you cannot get current around of it, so you have not much power either. So there is an optimum load resistance, and power out maximized when load resistance equal to internal resistance, in this case is 0.04 degree ohm. But you see the efficiency has a peak which is slightly different when the resistance is slightly higher, 0.0522 ohm. And this is exactly gamma times R for the ZT value that we put in. So you can see the optimum current, optimum loads for efficiency and power. You can even verify that. The ZT number for this thermoelectric was, Z for this thermoelectric was 0.00156. Medium temperature between hot and cold is 450. Z times T is 0.7, square root of 2 is 1.3. That means the ratio of the two resistances is 1.3, and that you can verify. So again, analytical result and numerical result match and give you a good intuition. You can even check the numbers. What are the values for efficiency at maximum power output and maximum efficiency? And again, you can check with the results you get from the program. You can see how these numbers for power output changes, for example, when you change delta T. Analytically, you saw that power output should go with delta T square, and here is a good case. You change the temperature on the hot side, power output. When temperature of the hot side goes up, power output goes up at power square, and you can verify the numbers at different delta T's. Efficiency goes up linearly, and again, you can verify that both numerically and using the analytical expression. The last problem of the homework had to do with the thermoelectric system cost analysis. So here's for example, a thermoelectric model. You assume a heat source, which is, in this case, we assume is coming from combustion, 1800 Kelvin. Cold side of it, we assume 800. That's actually very hot. The reason is thermoelectric here is a topping cycle. And in the lectures, you saw topping cycle is very advantageous for thermoelectrics. So 800 Kelvin is the steam temperature in the turbine. You can still apply a Rankine cycle to do a lot of work. But from these two temperature differences, you can get some work out of the thermoelectric. You assume you have 1000 by 1000 elements, field factor 0.1, that means 10% coverage, surfaces between the hot and the cold side. You have a heat concentration, a factor of 10. That means 10% of the surfaces is only covered by thermoelectrics. This program calculates the power output and the cost and everything, take into account a lot of the parasitics due to the heat spreading and so on we discuss in the lectures. At the end, you can calculate the power out for a given heat transfer coefficients and temperature versus ZT, or Z as a ZT as a uniqueness number. And you can see when ZT is 1, you can get something on the order of, let's say, 7000 watt per meter square. And when ZT becomes larger, you can see how this number goes up. You can change any of these parameters and see that you get the same curve. So basically improving ZT by reducing thermal conductivity or increasing Seebeck or increasing electroconductivity have the same effect. So from a power point of view, you don't see the effect and everything is superimposed. Then you play with, for example, heat transfer coefficient, and you see that with the same material ZT, of course, the higher is the heat transfer coefficient, the higher power output. Heat transfer coefficient plays a big role. You remember here, going from this point to this point, ZT goes from 2 to 6 or 8. This is huge improvement in material. But if you can deal with the higher heat fluxes, of course, you can get higher outputs at the same ZT. One of the last questions was, what is the thermoelectric system statement? Higher the heat transfer coefficient, this lower the power output generated. This is not correct. Higher heat transfer should give you higher power output. Optimum power output is only a function of the heat transfer coefficient, not the material property. That is not correct either. Optimum power output does not change with varying any of the 3 individual properties and the heat transfer coefficient as long as the ZT value remains the same. The part here which is wrong is the heat transfer coefficient. The correct answer is D. Optimum power does not change with varying any of the 3 individual material properties as long as ZT value and the heat transfer coefficient remain the same. So 2 parameters determine power generation: ZT, heat transfer coefficient. How about thermoelectric system cost? Some cost assumptions are given, and through this program you can verify. These are the ones that we discuss in week 4 cost analysis. Basically, if you start with a standard thermoelectric element, the costs could go down to 10 to 20 cents per watt. And if ZT goes up, this cost goes down. But here is a difference. Varying the thermal conductivity to improve ZT, or varying S or sigma, the power factor, have different cost implication. You saw that the efficiency did not depend how you improve ZT, but the cost depends. Why? Because we assume a constant cost. In this case, I assume was $500 per kilogram. When you improve ZT by lowering the thermal conductivity, automatically you also need lower amount of material to do thermal impedance matching. As a result, this is better to lower the cost than improving the power factor. If you improve the power factor, you don't change the amount of thermoelectric material to get the thermal impedance matching. So that's an important conclusion. Of course, if you have a material with lower performance than the existing material, because the thermoconductivity is higher or power factor are lower, again, you see the dependence is very different. You have an advantage to get a material with lower S and sigma, because that way at least you are not you don't need to get more thermoelectric material. So these are the options, 5 options for last question. Cost analysis. Material produces the same power cost if their ZT values are the same. That's not correct. In the high ZT regime, ZT bigger than 3, lowering the thermoconductivity is more desired than enhancing the power factor. The option C was a reverse of the 2, so one of the 2 should be correct. Power cost increases with increasing ZT. That's not correct. ZT increasing power cost goes down. Power cost decreases with decreasing efficiency. Of course, that's not correct. Decreasing efficiency, power increases. The answer is here. At the high ZT regime, it's better to reduce the thermoconductivity. Why? Because you need less material. So I hope you got an idea of how you can basically do some analytical calculation of heat balance in a thermoelectric system, and especially running these models for thermoelectric power generation, cooling, as well as cost. It's something that you can do simplified problems that was done here, but these are research tools. The assumption in these tools are the same ones that are used in the latest papers, so you can actually use these tools once you're familiar to calculate power or cost of realistic thermoelectric power generation. Good luck with your work.